Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIUA campus. Okay, let's discuss the lecture content first. In this video, we will cover Fourier series properties and discrete time Fourier series as well. And we will try to cover their properties as well. Okay, let's discuss properties of Fourier series. The periodic signal with its coefficients are usually represented as in this way. For example, you have a signal x of t, and if you take the Fourier series of that signal x of t, then you will get the coefficients ak, and these coefficients will constitute the Fourier series of that signal. For example, k can be 0, 1, 2, and so on. So these are the coefficients of the periodic signal a of t. The first property is the linearity. For example, you have a x and y. These are the two periodic signals with period t, and they have a Fourier series coefficients denoted by ak and bk respectively. That is, x of t has a Fourier series coefficients a of k, and y of t has a Fourier series coefficients b of k. Since xt and yt have the same period, it easily follows that any linear combination of the two signals will also be a periodic with period t. We want to show that by taking x, as you know that the x and y, they have the same period, and when we combine them linearly, for example, we combine them by adding them, these two signals, then in result we will get the Fourier coefficients which will be the summation of ak and bk. Let's see how it looks like. Furthermore, the Fourier series coefficients ck, for example, we name them instead of uh, when we add ak and bk, then the resultant Fourier series coefficients will be the ck, which will be the linear combination of xt and yt. That is, zt equals to axt plus by of t. A and b are some constants and are given by the same linear combination of the Fourier series coefficient of for xt and yt. That is, axt plus byt. If we take the Fourier series coefficients of the linear combination of axt and byt, then we will get the Fourier series coefficient ck, which will be the combination of ak plus b bk. So it means that they are linear. So this was the first property of the Fourier series called the linearity. The other important property is the time shifting. So we have to prove that what will happen if we shift the signal x of t by some time t naught. So what will be the effect on the Fourier series coefficients at the end? So let's see that after applying time shift to the periodic signal, the period of the signal is preserved. So you know that when the signal is periodic, if you give the signal a time shift of t, like a t naught, and it has the same period t, capital T. So even if you delay or if you have an advanced version of a signal, so it will not affect the overall time period of the signal. So for example, you have a signal x of t, and if you take the Fourier series, then you will get the coefficient a of k. And similarly, we name that the shifted version xt minus t naught as a yt. So when we take the Fourier series of the shifted version of the signal, time shifted version xt minus t naught, we got the Fourier series coefficients as a bk. So we name them as a bk. So let's find the bk of the shifted version of the signal xt minus t naught. So by using the formula which we already obtained from in the previous videos, so bk equals to 1 over t from for the time period integrate from the time period 0 to t xt minus t naught e minus jk omega naught t naught omega naught t. So when we let's say that t minus t naught equals to tau, let's say t minus t naught equals to tau. So replace t minus t naught here by tau, and then you have a t here, so t will be equivalent to tau plus t naught. So we will put here tau plus t naught. So e minus jk omega t tau plus t naught, and let's separate these two because these two are in the power, so we can just when they in exponential there is a addition in the power, so we can multiply them. So let's separate them. So x of tau e minus j k omega naught tau and e minus j k omega naught t naught t tau. So as you know that e minus j omega naught t naught is not a function of tau, so we can move this out from the integral. So we have e minus j omega naught t naught outside the integral equals to 1 over t x tau e minus j k omega naught tau d tau. So you know that this e x of tau e minus j k omega naught d tau is equivalent to ak. We previously into 1 over t is this term is equivalent to ak. We already have this equation. So ak into e minus j omega naught t naught. So from here we prove that when we have a time shift and we take the Fourier series of the time shifted version of a signal, then there is a no change in the Fourier series coefficients. However, we have a phase shift in the original signal. So no change in the magnitude of the Fourier series coefficient due to time delay. So Fourier series, when there is a time delay, there will be no change in the Fourier series coefficient. However, we will have a phase shift here because of a time delay. Another property is a time reversal. Time reversal means that you have to change the time from t to minus t. This is simply a time reversal. So let's see what is the impact on the Fourier series coefficients when we have a time reversal in the signal. So the period t of a periodic signal xt also remains unchanged when the signal undergoes time reversal. It should be in your mind that whenever we reverse the signal, then there is no change in the time period. Just there will be a time reversal, like uh, axis will be shifted, no change in the time period. To determine the Fourier series coefficients of yt, let we know name the x minus t as a yt. So now we want to find the Fourier series coefficient of yt. Let us consider the effect of time reversal on the synthesis equation. We named previously as a synthesis equation to find the Fourier series of a signal. So x of minus t equals to minus k is equal to minus infinity to infinity a k e minus j 2 pi t over capital T. Here you have a minus sign because of a small t. Because you change the sign here with a t with a minus t. So by replacing t with minus t, you got minus sign here. So making the substitution k equals to minus m, let's suppose that we have a k equals to minus m. So we obtain yt equals to x of minus t and replace when you replace k with minus m, so it becomes m is equal to minus infinity to infinity. There will be no change in the limit because it will be infinity to minus infinity or minus infinity to infinity is same. And replace here k with minus m, so we replace k with minus m, and when you replace k here with minus m, so you will get positive sign here, right? So we observe that the right hand side of this equation has the form of a Fourier series synthesis equation for x minus t. So this is the form of the Fourier series for the synthesis minus t x of minus t, where the Fourier series coefficient bkr. So let's say that the Fourier series coefficient bk equals to a minus k. So let's replace this bk with a minus k, for example. So that is, if xt is equal to ak, so it means that when we have a time reversal, so as you can notice from this equation, there is equivalent to the original synthesis equation, but with the you can notice that there is a time reversal in the Fourier coefficient a minus n. So when we replace with dk equals to a minus k, so it will be exactly equivalent to the original one, right? So it means that x minus t is when we have a time reversal, then there is a reversal in the time reversal in the Fourier coefficient as well. So there are, this is the general result, but there can be cases. For example, we have this as a general conclusion that when we have a time reversal, you will get the reverse in the Fourier series coefficient as well. Whereas when the signal x of t is even, there can be two cases, even and odd. So when signal is xt is even, so for even ak, when there is a time reversal, then ak is equivalent to a of minus k. So for the even case, there is ak is always equal to a minus k, so there will be no change, for example. Whereas for the odd case, when you have a time reversal, so ak is equivalent to minus a of a minus k. So this is some, these are the two cases that should be in your mind as well. Time scaling. So what will be the impact of a time scaling in the Fourier series? So it changes the period of the signal, but the Fourier coefficients remain the same. When you have scaled the signal, for example, you have a signal xt and you scale with some alpha uh, parameter, so you get x alpha t. So what will happen in the Fourier series coefficient? So you can prove that as well, but for simplicity, we are ignoring that proof here. So x alpha t equals to ak. So there is no change in the Fourier series coefficient, but we have a fundamental period which is changed from t to t over alpha. So time scaling will not change the Fourier series coefficients have not changed. Uh, However, the Fourier series representation has changed because the change in the fundamental frequency. Whenever the fundamental frequency changes, so the coefficients will change. The other property is the multiplication. When you multiply the two signal of different of the period, for example, t, xt and yt, these are the two signals. So in result, you will get the resultant Fourier series coefficients, which is equivalent to the product of a and b, because you have a Fourier series coefficients a for x of t and b for y of t. So summation of L equals to minus infinity to plus infinity AL bk minus L. So this is a kind of a discrete time convolution between the coefficients. So you, whenever you multiply the two signals, so in result, the Fourier series coefficients that you will get will be the multiplication, will be the convolution between the two coefficients, right? The other property is the conjunction and the conjugate symmetry. By taking the complex conjugate of the periodic signal, the effect is the time reversal and conjugation. Let's see. For example, you have xt and the Fourier series is a of k. So whenever you take the conjugate, so what will happen in to the Fourier series coefficients? Whenever you take the Fourier series of the x conjugate of t, then the coefficients will have a conjugate and the time reversal as well. So for there can be three cases in this scenario. For example, whenever you have a signal which is real, so in the Fourier series, a minus k is equivalent to a k's conjugate. So it is a conjugate symmetric. And the other case can be real and even. So the signal you are taking x of t is real and even as well. So whenever you take the Fourier series coefficient, then the result will be a k star, which is real and even. So it means that ak equals to ak star is real and even. Whenever the signal is real and odd, so the Fourier coefficients will be ak is equivalent to minus ak star. It means that they are purely imaginary and odd, and whereas the a naught is equal to 0. The other important concept is the Parseval relation for the continuous time periodic system. What does this equation tells us? It's very simple. It looks, although it looks a bit complicated, but it's very simple. The relationship is given as that. The left hand side of the equation is, you are very much familiar with this equation. This is equivalent to the average power of a signal. So whenever you have a time domain signal, right? Time domain, you can take the average power in this way. Whereas Parseval says that in frequency domain, because you know that the Fourier series give us the signal in frequency domain. So whenever you have a frequency domain signal, how can you find the average power? He just say that the average power in time domain is equivalent to summation of the Fourier series coefficients, summation and the power of the Fourier series coefficients. So whenever you sum whenever you take the Fourier series coefficient, take its amplitude and then square it. So it means that uh, its amplitude is squared, and then you sum these different amplitudes. In result, you will get the average power. So it means that total average power is equal to sum of average power in all harmonic components, because AK, A, A0, A1, A2, A3, these are harmonics. So energy in time domain equals to energy in frequency domain. So it proves that energy in time domain is equal to energy in frequency domain as well. Okay, there is one example to uh, this example is just to prove the benefits of the properties which we already discussed. For example, we have a property of linearity, we have a property of time scaling, so on, time shifting. So now in this example, we will apply these properties, and we will show that the application of these properties will simplify the calculation. For example, you have a signal g of t, which is represented as xt minus 1 minus 1 over 2. So this is mathematical representation of the signal g of t. So consider the signal with a fundamental period of 4. The signal given here has the fundamental period of 4. It means that capital T equals to 4. And uh, we could determine the Fourier series representation of GT directly from analysis equation. So it is easy to determine the Fourier series of GT by directly using the analysis equation, which we already studied, analysis and the synthesis equation. However, in this example, we will focus on the uh, properties. So how can we solve the same series by using different properties? How can we find the Fourier series by using different properties, right? So first, you know that xt minus 1, there is a time shift of 1, right? So we can divide this into two parts, xt minus 1 and minus 1 by 2. So these are the two different parts, right? This one and this one, to apply the property, right? So first of all, the time shift property indicates that this is the time shift property. If you shift the signal in time domain, then by whenever you take the Fourier series in the frequency domain, you will have a same Fourier series components, but there will be a phase shift, right? So the time shift indicates that if the Fourier coefficient of xt are denoted by ak, the Fourier coefficient of xt minus 1 may be expressed as this one. So bk is equal to ak, right, by using this one, e minus jk by k pi by 2. How we get the k pi by 2? If you put here time period as a 4, so 2 over 4 you will get pi by 2. So it's equivalent to bk equals to ak e minus j k pi by 2, right? So you get the Fourier series coefficient bk equal to this one. So the Fourier series coefficient of the DC offset, the other term was minus 1 by 2. This is the DC offset. There is no other term except DC component. So on the right hand side of the equation, so you can write that DC offset Ck equals to 0 for k not equal to 0. So when k is not equal to 0, it means that because this is a DC component, DC offset value, just it has impact on k equal to 0. So for k not equal to 0, it always will be 0. So now we can apply the linearity property. We have a two different coefficients, ck and bk. So by applying the linearity property, you know that ak plus bk is equal to ck. So here we have a ak minus bk equals to bk minus ck equals to tk. So applying the linearity property, we conclude that the coefficient for gt may be expressed as this one, dk, we renamed as a dk, which is the sum of bk minus, because we have a minus sign here, minus dk. So bk, we have a ak minus for k not equal to 0, ak minus j k pi by 2 minus 0, so minus 0 has no effect, right? The other will be a naught, sorry, it's a bk plus ck, right? Plus 0, so no effect. And ak for the other point, for k equals to 0, for the DC term, you know that DC term is represented as a naught. So A naught minus, this is already minus A naught minus 1 by 2, right? So where each AK, because AK also have some value which we already proved for the square wave in the previous examples. So where each AK may now be replaced by the corresponding expression from equation. This is equation which we already solved in the previous examples in the previous video. So we will get dk by replacing ak with sine pi k by 2 over k pi e minus j k pi by 2 over for k not equal to 0, and for k equal to 0 it will be 0 because a naught is 1 by 2. So 1 by 2 minus 1 by 2 is 0. So finally we get dk equals to 0. Okay, let's discuss the concept of a discrete time Fourier series. The concept of the discrete time Fourier series is almost similar to the continuous time Fourier series, except some representation differentiation between them, right? So, discrete time Fourier series of a discrete time periodic signal is finite series. For discrete time, it is a finite, whereas as opposed to the infinite series representation required for a continuous time periodic signal. For example, you have a xn, so you have a xn, and it is similar to the value equal to xn plus n, where n is the period. So it will repeat after n. For example, you can plot this, this, and after some period, for example, n equals to 1, it will repeat again this, 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 so so on. It will carry on in this way, right? In this way. And omega naught is equal to 2 pi by n. Set of all discrete time complex exponential with the same period n. So we can write the complex exponential phi k n equals to e j k omega naught n, and where for omega naught, if you can replace 2 pi by n, so e j k 2 pi over n small n k, right? And where k equals to 0, plus minus 1, plus minus 2, and so on. So for each value of n, the k will be repeated. For example, the number of components you have, right? So in the above, there are only n distinct signals. N means the n period with n period. So phi k plus n is, because you know that xn is equal to xn plus 1. So that will repeat after each period. So for phi equals phi k plus n equals to e j k plus n. Instead of k, you put k plus n omega naught n. So just separate them, and then ej omega naught n, and ej instead of omega naught put 2 pi by n, which is uh, you can write that in this way, and n will be the cancel out. So you can write ej 2 pi n, and ej 2 pi n is 1 because of Euler's identity. So you will get ej omega naught n, which is equal to phi k n. So it means that the value of phi k plus n, with when you repeat after some period, it will always be equivalent to phi k n. So the component will be equivalent. Let's discuss how we can represent the discrete time signal in terms of a periodic signal. So we wish to consider the representation of more general periodic sequences in terms of a linear combination of sequences this one. Phi kn is a complex exponential, as we already defined. Such a linear combination has formed this one. For example, if you want to express some periodic signal x of n in terms of a Fourier series, and the signal is discrete, right? How can you represent? So there will be a ak coefficients, and phi kn is the complex exponential. And you will iterate, there is a summation, iterate from for k, there will be k iteration, right? K means k equals to 1, 2, up to n, right? So equals to k, ak, instead of phi kn, you can put the complex exponential, which is ej k omega naught n. And then k equals to, instead of omega naught, we have a period of 2 pi over n, right? Since the sequences are distinct only over range of n successive values of k, we have already studied that because this is a discrete time signal and it repeats after n period, and if you repeat after n period, the sequences will be same, right? So the only difference is when between the sequences are from k equals to 1 to n, 0 to n, for example, 0 to n minus 1, right? So the sequences are different. But for other, if you repeat again after n period, the sequences will be same. So instead of doing infinity, we have only n sequences here. The summation in equation 3.97, this one, uh, need only include in terms of over the range. So we have to evaluate over the range n. Thus the summation is on k as k varies over a range of n successive integers. So k varies over n successive integers, beginning with any value of k. Beginning with any value of k means k can be started from 0 to n minus 1, or k can be started from 3 to n plus 2. It doesn't matter because they are same, but the starting point can be different. We indicate this by expressing the limits of summation as k equals to n. So what does it mean? That it means instead of saying infinity, so we can say that k is always equals to n, right? The range is between n and the starting point can be any. So we just write in this way. For example, k could be any values from 0 to n minus 1, k can be from 3 to n plus 1. In either case, by virtue of this equation we already discussed, exactly the same set of complex exponential sequences appears in the summation. So on the right hand side of this equation. Equation 3.88 is referred to as, this equation is referred as the discrete time Fourier series. So this is your discrete time Fourier series, and the coefficients AK are the Fourier series coefficients. Let's summarize the discrete time Fourier series. How can we evaluate the discrete time Fourier series? This provides a closed form expressions for obtaining the Fourier series coefficients, and we have the discrete time Fourier series pair as xn, and this is your 3.94 equation is the synthesis equation, whereas the Fourier series coefficients ak can be found by using this equation. Here the period is from n equals to varies from here the n varies from 1 to n, whereas in synthesis equation the k varies from 1 to n. So you can find the xn and ak using 3.94 and 95 equation. Let's discuss the example one related to discrete time Fourier series. We have a signal that repeats with a period n equals to 6, right? And the value ranges, we have given signal minus 5, we have a value 1, minus 4, 0, and up to minus 2, 0, minus 1. Then again we have a value 1 and 0, 1, and so on. Up to 5, we have repetition again. So we have a period of n equals to 6. So omega naught, you know, that is the 2 pi over n. So n is 6 here, so we put the value of 6, so omega naught is pi over 3. To find ak, to find the Fourier series coefficients, as we know that it's varied from, it's equal to 1 over n equals to 1 to n, x of n, e minus j omega naught kn. So here we have a period of 6, so 1 over 6, and due to periodicity, we consider the period. We can consider any period from 0 to 6, or from 0 to 5, or from 1 to 6, anywhere, because this is a periodic. But we are taking the signal from minus 2 to this point 3. So this is total 6 points: 1, 2, 3, 4, 5, and 6. So period is 6. So from minus 2 to 3, we are evaluating this signal. And x of n e minus j omega naught kn. Let's put the values for the x of n for different values of the n. For n is equal to minus 2, we have no value here, our output is 0. So xn is 0, so we have a 0 here. For n equals to minus 1, we have a 1 here, and 1 into 1 by 6, so 1 by 6 into 1 e minus j omega naught k, and instead of n we are putting minus 1 here, so minus 1 plus 1 over 6 again into 1, because at 0 we have a 1, and e minus 0, it becomes 1, right? And plus 1 over 6 again, due to uh, position 1, and 1 into minus e minus j omega naught into k, and we have a 1. So we put 1 here. And for the rest of the values 2 and 3 we have 0, 0, right? Now let's move on. So we can remove the value 0, 0, and we have a remaining 4 values, right? 3 values, sorry, 1, 2, and 3. So let's rearrange them, and in terms of omega naught k and minus omega naught k. So 1 over 6 e j omega naught k plus 1 over 6 is constant. Then 1 over 6 e minus j omega naught k. If we write this equation again, 1 over 6 plus 1 over 6, taking common 1 over 6, so we have e j omega naught k plus e minus j omega naught k. You know that if it is divided by 2, then it is equivalent to cos omega naught k. So as there is no 2 here, so it means we are multiplying by 2. So when we multiply by 2 and divide by 2, so multiply and divide by 2, so it becomes cos omega naught k, and uh, here due to multiplication by 2 it's become 1 over 3. So 1 over 6 plus 1 over 3 uh, cos omega naught k. So this is our result. So 1 over 6 plus 1 over 3 cos omega naught k. In terms of in place of omega naught, we are putting here 2 pi by, or omega naught is pi by 3, so pi by 3 k. Now to find the values of ak, different values of k, because this was a general equation for ak, but k can be varied from 0 to n. So here we have a period of 6. So and the k is, let's take the values of k at 0. So it becomes a0. So put the value of k here. So it becomes cos of 0. So 1 over 6 plus 1 over 3 cos 0 is 1 over 2. For k equals to 1, we have a1, 1 over 6 plus this is equal to 1 over 3. By taking the cos pi by 3, its result is 1 by 2. So by putting this value, we get 1 over 3. For k equals to minus 1, because we have a value at minus 1 as well. So minus 1, so a minus 1 equals to a1 by symmetry of xn. So it becomes a minus 1 is equal to 1 over 3. So both of them have same value because of symmetry. And k equals to 2, put value of 2 here, so we get 0. And similarly by symmetry, we have a minus 2 equals to a2. And a3, we have 1 over 6, 2 cos pi is minus 1, so minus 1 by 6. So in this way we find the result of our uh, periodic signal. We find the Fourier series coefficients, and our period was from minus 2 to 3, right? So we find all the values from minus 2 to 3, right, for the period 6. So we have a 6 coefficients. Let's take another example, which is x of n. We have a signal given as this one, 1 plus sine 2 pi n into n plus 3 cos 2 pi n over into n cos 4 by n plus pi by 2. The signal is periodic, as you know that, with period n, and as an example we can expand xn directly in terms of complex exponential. We already did it for the continuous time case. We can directly expand this equation sine 2 pi n in terms of a exponential, because it is equivalent to 1 over 2j ej 2 pi n over n minus e minus j 2 pi n over into n plus 3 by 2 into this one by evaluating cos. Instead of cos, we are putting the exponential. And similarly for cos 4 pi n by n plus pi by 2, we are evaluating in this way. So collecting terms, we find that because we are gathering each similar types of term here and similar types of here and similar here and this one. So by comparing this with our Fourier series equation, we can get the Fourier series coefficients for different value of k. So a naught, for it means for k equals to 0, we have a value of 1, and for a1, because we have a k equals to 1 here, we have a these coefficients, right? And because of minus sign here, so we have a minus 1 this one. And because of positive sign, and we have a 2 here, so it means we have a k2 here. So a2 equals to 1 over 2, right? 1 over 2j. And for a minus 2, we have a minus 2 here, so we have 1 over 2 minus 1 over 2j, because we evaluate this one e minus j pi by 2 by using Euler's identity. If you open this one, you will get the result minus j, right? So minus j into 1 over 2, you will get minus 1 over 2j. And for other values of ak, it is 0, because we don't have other values, like we don't have a j3 term, j4 term. It means that other coefficients are 0. Now, real and imaginary parts of the Fourier coefficients for period n. Real and imaginary parts, it means that if you have a ak, as in the previous slides we have, so we have the term with no j sign, for example half, 3 by 2, so these terms are called real terms. Where imaginary terms are the terms which we have a j, like j terms. So we are independently plotting them for 0 to n period, right? So we have a value at 0, 1, which is, and 3 by 2 and minus 1. So 1 and minus 1 we have a real values, and similarly imaginary values we have in this way. And these are repeating after n period, n to n. You can see that the results are same. There are no difference between them. So overall your coefficients will repeat after period of n to n and minus n to n, similarly for imaginary part as well. Now magnitude and phase of the coefficients. So magnitude means that if you have a amplitude, if you have a you have imaginary and real part, so it will be real square plus imaginary square under root. This will be your complex imaginary square. This will be your amplitude, right? So in this way, we have a1 values, we will take the amplitude and then square root. So we are plotting this here as well. And for the theta angle phase, we are plotting as theta is equal to tangent inverse b over a, right? If you put the values of tangent inverse and b over a here, you can get the angle, right? B over A means B is your imaginary part and A is your real part. So you can just notice here that you will get these types of plot for the values given. For range A0, A1, we have actually 5 terms: A0, A1, A minus 1, A minus 2, A2. So we have 5 terms here. So we are plotting the phase here, and then it is repeating after period n, and then it is repeating after period 2n. So properties of discrete time Fourier series, as we already discussed and proved these properties for the continuous time Fourier series. For the discrete time Fourier series, the properties are almost similar. Like linearity, we studied in the case of continuous time case. So similarly, for discrete time case, we have a linearity property as well. Time shifting, here we also have a time shifting. Frequency shifting, conjunction, time reversal, time scaling, and so on. There can be number of properties in discrete time, but we are mentioning here some just for an example that the continuous time properties and discrete time properties are almost similar. Thank you for listening, and for Q&A session, we have an online separate session. Thank you very much.